Hello everybody, this is Mika Seppälä. The picture on the cover page of this lecture reminds us that we have already discussed the problem of finding the slope of a tangent line of a graph of a curve. That problem led to the concept of the derivative. In this lecture I will introduce derivatives again, now slightly more mathematically than before. I will give examples and discuss properties of derivatives. In this lecture we define the derivative of a function, starting from the derivative of a function at one point and then going to functions which are derivatives of other functions. We consider examples, compute slopes of tangent lines and compute equations of tangent lines, and then we discuss derivatives graphically. To compute the slope of the line tangent to the graph of a given function f at a given point x0, f of x0, one has to compute the limit of the quantity f at x0 plus h minus f at x0 divided by h, and the limit as h approaches 0. If this limit exists and if it is finite, then we say that the function f has derivative at the point x0 and that this limit is the derivative of the function f. The derivative of the function f gives also the slope of the line tangent to the graph of the function f at the point x0, f of x0. We use the following notations for the derivative of the function f at the point x0. The first and maybe the most common notation is read f prime at x0. Then we use the notation which looks like a fraction, df at x0 dx. This is not a fraction, it is read df dx. And then we use the differential operator capital D. Capital D f and then x0 in parentheses, or capital D and f in parentheses followed by x0 in parentheses. They all denote the derivative of the function f at the point x0. If the function f has derivative at each point of its domain of definition, then we can associate to the function f the function whose value at every point x is the derivative of f at x. This function is the derivative function of the original function f. It is usually simply called the derivative of f. Notations for the derivative of f are f prime, df dx, capital D followed by f, capital D followed by f in parentheses. As the first example, let us compute the derivative function of the function x squared. Computing by the definition, the derivative of the function f equals x squared at the point x is the limit of x plus h squared minus x squared divided by h, and the limit as h approaches 0. Expanding the brackets in the numerator, we get the limit as h approaches 0 of x squared plus 2 times h times x plus h squared minus x squared divided by h. Here in the numerator x squared cancels out and we are left with 2 times h times x plus h squared, and that divided by h. Now h cancels out and we are left with 2 times x plus h. The limit of this expression as h approaches 0 is simply 2 times x. We conclude that the derivative function of the function x squared is f prime of x equals 2 times x. As a second example, let us compute the derivative function of the function square root of x. Again, computing by the definition, we see that the derivative function of square root of x at the point x takes the value limit as h approaches 0 of the fraction square root x plus h minus square root of x divided by h. To compute this limit, one has to multiply and divide by the conjugate of the square root expression in the numerator. Hence, one multiplies and divides by square root x plus h plus square root of x. When one does this, the whole expression remains unchanged, and this leads to a simplification because the numerator becomes simply square root x plus h squared minus square root of x squared. So the numerator is x plus h minus x. The denominator remains at h times square root x plus h plus square root of x. But the numerator simplifies to h, and the h in the denominator cancels out. And therefore we may conclude that the limit of the original expression square root x plus h minus square root of x divided by h, as h approaches 0, is simply 1 divided by 2 times square root of x. We conclude that the derivative function of the function square root of x is 1 divided by 2 times square root of x. We were led to derivatives by the problem of defining and computing the slope of the line tangent to the graph of a given function at a given point. The derivative of the function is the slope of the line tangent to the graph at that corresponding point. Therefore, to compute the equation of the line tangent to the graph of a function f at the point a, f of a, one simply observes that the slope is given by the derivative f prime at a, and that the line passes through the point a, f at a. The equation of such a line is y minus f of a equals f prime at a times x minus a. This can be simplified to y equals f prime at a times x minus a times f prime at a plus f at a. This is the equation of the line tangent to the graph of the function f at the point a, f of a. As an example of this computation, let us compute the equation of the line tangent to the graph of the exponential function f of x equals e to the power x at x equals 1. Here we have two problems. The first one is to compute the derivative of the exponential function at x equals 1, and secondly to compute the equation of the tangent line using the formula given just a moment ago. To compute the derivative of f at 1, observe that this derivative is, by the definition, the limit as h approaches 0 of the expression e to the 1 plus h minus e to the 1 divided by h. Now, e to the 1 plus h is e times e to the h, and e to the power 1 is simply e times e to the power 0. So in the numerator, we may take e as a common factor. And this multiplicative factor of the numerator can be taken outside of the limit computation. And we observe that the derivative of the exponential function at the point x equals 1 is e times limit as h approaches 0 of the quantity e to the power 0 plus h minus e to the power 0 divided by h. Now we must remember that the definition of the number e, the mathematical constant e, was such that the slope of the line tangent to the graph of the function e to the power x at x equals 0 is 1. Now the limit of e to the power 0 plus h minus e to the power 0 divided by h as h approaches 0 gives the slope of the line tangent to the exponential function at x equals 0. Therefore, this limit by the definition of the mathematical constant e is 1. And we conclude that the derivative of the exponential function at the point x equals 1 is simply e. The problem was to compute the equation of the line tangent to the graph of the exponential function e to the power x at x equals 1. We now know that the slope of this line is e. We also know that it goes through the point 1e. Therefore, using the formula y minus f of a equals f prime at a times x minus a, we get the equation y minus e equals e times x minus 1 for the line tangent to the graph of e to the x at x equals 1. This equation y minus e equals e times x minus 1 simplifies just to y equals e times x. So this is the equation for the line tangent to the graph of the exponential function at the point 1, e. In the final problem, two graphs are given, and we know that one of these graphs is the graph of a function and that the other one is the graph of its derivative. We have to decide which is which. Is the blue curve the function and the red curve its derivative, or vice versa? To find out whether the blue curve is a graph of the function or the red curve, we have to look at some special points. So it is convenient to first look at points where the tangent line of the function is horizontal. At such points, the derivative must take value 0. Now, the red curve has a horizontal tangent at the maximum point and at the minimum point shown in this picture, and at those points the blue curve doesn't seem to take the value 0. On the other hand, whenever the blue curve has some kind of a local maximum point where the derivative should be 0, that is the tangent horizontal, the red curve appears to intersect the x-axis, and therefore we conclude that the red curve is the derivative and that blue curve is the function. So answer is the blue graph is a graph of the function, the red curve that of its derivative. Last example, we use the fact that if a function takes a local maximum value, which is such a value that nearby it doesn't take larger values than at that local maximum value, or if the function takes a local minimum value, then the tangent must be horizontal. That is, the derivative must be 0. This seems almost obvious, clear by looking at the picture. We will make this precise and prove these facts later on in subsequent lectures. But for the moment I sign off. Goodbye.